Welcome. This presentation will provide an educational overview on the topic of how self-driving cars work. We will begin by establishing the fundamentals of autonomous driving to provide a clear foundational understanding. So, what are self-driving cars? By definition, they are autonomous vehicles capable of sensing their environment and operating with minimal human input. This is achieved through a combination of core components, sensors, maps, and AI, which allow the vehicle to perceive, decide, and control its movement. The industry uses the SAE levels, a global standard for categorizing automation from no assistance to full self-driving capability. As for the current status, most consumer vehicles offer partial automation, while full autonomy remains limited to specific geographical areas. Let's examine the sensor suite, which functions as the car's eyes. Cameras capture high-resolution images of lanes, traffic lights, signs, and other road users. LiDAR technology emits laser pulses to build detailed 3D maps and measure distances to objects. Radar uses radio waves to determine an object's distance and speed and is especially effective in adverse weather. Finally, GPS and HD maps provide the system with a comprehensive pre-existing understanding of road features, boundaries, and speed limits. Now that we have covered the sensory inputs, we will proceed to discuss the intelligence behind the wheel. Let's begin with the core functions of perception and prediction. The process commences with data integration, where raw sensor data streams into powerful onboard computers for subsequent processing and analysis. Following this, AI algorithms, including deep learning, perform object identification to recognize pedestrians, vehicles, and road markings. Concurrently, neural networks, trained on vast datasets, engage in pattern recognition to interpret complex driving scenarios. Finally, the system predicts future behavior, forecasting the likely actions of surrounding entities by using past behavior and probability models. Now, let us examine planning, control, and the requisite hardware. After perceiving the environment, the software engages in action planning, where it formulates optimal maneuvers based on the collected data and predictions. These plans are then converted into precise commands for the steering, throttle, and brake systems through a process known as vehicle actuation. This is all made possible by substantial computing power, with high-performance CPUs and GPUs optimized for real-time AI processing. To ensure safety, system redundancy is critical, incorporating backup components like computers and brakes for reliability. Turning to development, challenges, and benefits. The AI training process is extensive, logging millions of real-world miles and billions of miles in simulation for skill development. This facilitates a process of iterative improvement, as AI systems are constantly updated, tested, and refined. However, there are operational challenges, as the technology faces hurdles from bad weather, human unpredictability, and complex sites. Broader hurdles also exist, such as addressing safety validation, cybersecurity, liability, regulations, and ethical dilemmas. Nevertheless, the benefits are significant, including improved safety and efficiency, with the potential to reduce crashes and improve traffic flow, as well as enhanced mobility for non-drivers and the creation of new business models. This brings us to the future of driving autonomous vehicles. We are truly witnessing a major innovation on the road ahead.